Deep beneath your feet, in rock that formed when dinosaurs still ruled the continents, there are tiny metal spheres that should not exist. They are perfectly smooth, in a way that ordinary geology almost never produces, clustered in layers that match moments of global crisis and mass extinction. Under a microscope, they look eerily familiar to modern industrial byproducts, as if someone had already built factories, burned fuel, and left behind dust that rained out of an ancient sky. Yet these layers are more than 65 million years old. They predate every city, every farm, every human story. If they really are artificial, then our entire timeline is wrong, and we are not the first technological species to shake this planet. The only way to find out is to climb into Earth's memory and see how much it is still willing to tell us. For most of our history, we assume that memory was simple. Earth began as fire and stone. Life appeared, evolved slowly, and eventually produced us, the one species capable of building a global civilization and rewriting the surface of the planet. Everything important, we thought, happened recently. Our industrial age is only a few centuries old. Our presence in the fossil record, if anyone ever reads it in the far future, would be a brief flash of change, quickly smoothed out by erosion and time. Against 4.5 billion years of history, what could a few hundred years really matter? The trouble is that Earth has already proven it can keep secrets, then reveal them in ways that overturn everything we thought we knew. In the 1970s, a physicist named Luis Alvarez and his team were not trying to find lost civilizations. They were trying to solve a different mystery, the one about how the dinosaurs died. They studied a thin layer of clay at the boundary between the Cretaceous and the Paleogene periods, and they found something strange. That clay was enriched with the element iridium, far beyond normal levels in Earth's crust. Iridium is common in meteorites, rare in surface rock, and there it was, smeared in a global ring that matched the timing of a mass extinction. From that clue, Alvarez and his colleagues proposed what now feels obvious, that a massive asteroid struck Earth about 65 million years ago, kicked dust and vapor into the atmosphere, and triggered a planetary winter. At first, many geologists resisted the idea. A single impact, reshaping life worldwide, sounded too dramatic. Yet as more evidence came in, the story became unavoidable. The iridium layer was present on multiple continents. Craters of the right age and size were found, shocked quartz, tiny deformed crystals that form under extreme pressure, appeared in the same horizon. In the end, a thin band of clay less than a centimetre thick forced us to accept that Earth's history includes sudden, violent events that leave precise chemical fingerprints. That discovery matters here because it proves two crucial things. First, the planet is capable of preserving a record of global catastrophe for tens of millions of years. Second, when we finally learn how to read that record, we can reconstruct stories we never imagined. A single unusual element in a layer of rock was enough to reveal an impact that darkened the world and wiped out most large animals on land. If one asteroid can leave such a clear trace, then a planetary civilization burning fuel, refining metals, and reshaping ecosystems should leave traces as well. The question is whether we would recognize them, or whether we would mistake them for natural change. This is where the Silurian hypothesis enters the story. It is named after a fictional intelligent reptile species from an old science fiction series, but the idea itself is very real and very serious. It asks a simple and unsettling question. If an industrial civilization had existed on Earth long before humans, would we be able to detect it in the geological record? Not from surviving cities or machines, which would have long since crumbled away, but from changes in chemistry, climate, and the distribution of life. In other words, if someone else once dug mines, burned fuel, and filled the air with strange compounds, how would that look after tens of millions of years of erosion, burial, and tectonic recycling? At first, the answer seems obvious. Of course we would see them. Modern industry is not subtle. We release greenhouse gases, heavy metals, and synthetic compounds that never existed before. We alter coastlines, dam rivers, strip forests, and pour concrete over entire regions. Surely such a transformation would stand out clearly forever. Yet when you zoom out to Earth's full timescale, that confidence starts to crumble. Our fossil fuel era is less than 3 human lifetimes old. Our industrial activities will probably last, in their current intense form, for only a few centuries more, if that. Compared to the age of the planet, this is a microscopic flash. Imagine compressing all of Earth's history into a single calendar year. On that scale, the planet forms in early January, the first simple cells arrive in spring, and complex multicellular life appears around late November. Dinosaurs dominate until a few days before the end of the year. Modern humans show up in the last minutes of December 31st. Our Industrial Revolution, the period with smokestacks and power plants and satellites, occupies the final fraction of a second before midnight. If civilizations before us also had industrial ages that burned hot and fast, their entire technological story could be squeezed into that same sliver of time, then buried beneath new layers of rock and ocean. This is the core difficulty that drove the Silurian hypothesis from a playful thought experiment into a serious scientific challenge. We know exactly what we are doing to Earth right now. We can measure the carbon dioxide in the air, the microplastics in the ocean, and the radioactive isotopes in soil and ice. We can predict that some of these signatures will persist for tens of thousands of years, maybe longer. But 4.5 billion years is not tens of thousands of years. It is an unimaginably deep ocean of time in which continents wander, mountains rise and crumble, and old seafloors are dragged down into the mantle and melted. Geologists understand this through the rock cycle. A sediment that settles on the seafloor today might be buried, compressed into stone, uplifted into a mountain range, and then eroded back into grains that wash to the sea again. Most traces of any specific moment are destroyed bit by bit through this process. Only certain environments, like deep ocean basins, lake beds, and polar ice, offer stable archives that can last for millions of years. Even then, those archives are patchy. They give us snapshots rather than continuous video. Whole chapters of Earth's story are simply gone. When you look at that patchy record, you see something both frustrating and hopeful. Frustrating because it means an earlier industrial age could be almost completely erased by time. Hopeful because we also know that some things do survive extremely well. Unusual isotope ratios, sudden shifts in carbon locked into rocks, layers that show sharp changes in temperature or ocean acidity. These are the kinds of clues we have already learned to read from events like the asteroid impact that ended the age of dinosaurs, or massive volcanic outpourings that choked the sky with ash. Our task, if we really want to know whether we are first, is to ask whether any of those clues look different from what natural processes alone would produce. We need to separate the fingerprints of volcanoes, impacts, and slow climate cycles from the possible fingerprints of cities and industry. The Silurian hypothesis does not claim that such civilizations definitely existed. It simply insists that we take the question seriously and ask what evidence would convince us either way. In doing so, it turns Earth into a kind of detective novel, with the rocks as pages that have been burned, torn, and rewritten over impossibly long spans of time. As we pull on this thread, another question appears. If it is so hard to see even our own impact projected into the deep future, how many other stories might have already come and gone without leaving an obvious trace? Paleontologists already talk about gaps in the fossil record, stretches where evolution seems to pause and then suddenly jump ahead, as if chapters are missing. For now, we will leave those mysteries for later parts of this journey. In this opening hour, we are going to focus on one central problem. What does a civilization actually look like after tens of millions of years underground? And would we have the courage to admit it if we found it? To explore that, we will follow 3 threads. First, how human industry would appear if some future species examined our rocks and ice long after we are gone. Second, what we already know about abrupt changes in Earth's past that might resemble that kind of signature. Third, how deep time might distort or hide those signals so completely that even a careful geologist could miss them. Along the way, I invite you to imagine that you are that future investigator, holding cores of ancient sediment in your hands and trying to decide whether the patterns inside are natural or deliberate. As we do that together, the line between science and science fiction will start to blur in unsettling ways. The metal spheres that open this story are a perfect example of how that blurring begins. To a geologist who expects only natural processes, they can be explained as the result of intense heating, melting, and rapid cooling during an impact or large volcanic eruption. To an engineer, they look suspiciously like the micro-scale droplets of slag and pollution that modern factories produce. The chemistry locked inside them will decide which story is closer to the truth, and as we start to examine those details, we will find ourselves forced to confront a possibility that is at once thrilling and terrifying. That Earth has hosted not just one industrial age, but many, and that ours may simply be the first one to realize it. To understand why that possibility is not as far-fetched as it sounds, we need to look closely at how life itself appears in the rocks. When most people imagine evolution, they picture a smooth, continuous story. Simple things gradually become more complex. Fins slowly turn into legs, and one species shades into the next across endless time. It feels like watching a slow-motion film. But the actual fossil record is not a smooth movie. It is more like a series of snapshots with whole scenes missing between them. Paleontologists have known this for generations. When they dig through layers of rock, they expect gaps, simply because fossilization is rare. Most organisms never become fossils. They decay, are eaten, or are destroyed by heat and pressure before they can be preserved. Even when bones or shells are buried, conditions have to be just right for them to survive long enough for us to discover them. So straight away, the archive we rely on is biased. This idea is called preservation bias, and it makes perfect sense. Creatures that live in or near water, with hard parts like shells or bones, are far more likely to fossilize than soft-bodied animals in dry environments. Large populations leave more remains than rare species. Some places, like river deltas and deep-sea sediments, are far better at storing fossils than mountain slopes or desert dunes. When you put all of that together, you expect a fossil record that is incomplete and uneven. For a long time, those basic limitations were enough to explain most of the gaps. If a species appears suddenly in the rocks, the reasoning went, it probably means we simply have not yet found the earlier, more primitive forms. As more fossils are discovered, the story should smooth out. But that is not always what happens. In some of the most important transitions in Earth's history, the jumps stay sharp even as we add more data. The most famous example is something called the Cambrian explosion. Around 540 million years ago, in a relatively short geological interval, complex animals with hard skeletons and diverse body plans show up all over the world. Before this, the fossil record is dominated by simpler life. After it, the ocean suddenly teems with recognizable ancestors of many modern groups. From the point of view of deep time, the Cambrian explosion may have unfolded over a few tens of millions of years. That is not instant in any human sense, but compared to the hundreds of millions of years of slow change before and after, it looks like a firework going off in the dark. Entire body plans appear, spread, and diversify with astonishing speed. It is as if evolution slammed down the accelerator. Scientists have proposed many explanations. Maybe oxygen levels in the oceans rose past a critical threshold, allowing larger and more active animals to thrive. Maybe ecological arms races, with predators and prey pushing each other to evolve defenses and weapons, drove rapid innovation. Maybe the earlier stages of evolution simply did not preserve well, because early creatures lacked hard parts and lived in environments that rarely fossilize. All of those ideas probably carry some truth. Natural systems often stay quiet until a threshold is reached, then change dramatically. Still, even after decades of work, the Cambrian explosion retains an air of mystery. When you look at the layers where these animals appear, you do not see a gentle fade in. In many places they just show up, fully built, with muscles, eyes and armour, and then quickly radiate into a dizzying variety of forms. As we move forward in time, we encounter other jumps that feel similar in spirit, even if they are less famous. Plant life makes sudden moves onto land. Flowering plants spread rapidly and take over ecosystems. Mammals, long small and marginal during the age of dinosaurs, suddenly diversify into whales, flying bats, giant ground dwellers, and primates after the asteroid impact clears ecological space.
Again, there are natural explanations, and they are compelling. Environmental pressures, mass extinctions, and changing climates create both challenges and opportunities for evolution. When an old world collapses, new forms can surge in to fill the void. You do not need a hidden civilization to explain that pattern. At the same time, if you were looking for places where an advanced species might have intervened, these are exactly the kinds of transitions you would examine more closely. Think for a moment like a planetary engineer rather than a paleontologist. If you wanted to reboot an ecosystem after a catastrophe or speed up the development of more complex life, you would not necessarily build metal machines and roads. You might choose to plant genetic seeds, engineered organisms that can spread and adapt on their own. To someone reading the fossil record later, that intervention might look like a sudden evolutionary burst, even if every step was carefully designed. This does not mean that the Cambrian explosion or later radiations were artificial. What it does mean is that the fossil record alone is a blunt tool for distinguishing between a natural evolutionary threshold and a deliberate push. Both can produce similar visible patterns, where new forms appear rapidly and then settle into long periods of relative stability. To go further, we need to look at the chemistry and structure of those fossils in fine detail. Researchers already do this when they analyze things like growth rings in fossil shells, microstructures in bones, or the isotopic signature of the elements trapped inside. These clues can reveal whether ancient animals lived in warm or cold water, whether they experienced seasonal cycles, and what they ate. If someone had engineered those organisms, especially using technology more advanced than our own, would we see hints of that in their molecular makeup? Modern genetic engineering leaves fingerprints. We use specific tools and patterns that can, in principle, be recognized by anyone who understands them. But a civilization millions of years ahead of us might not. They could design life at a level that blends seamlessly into what we think of as natural variation. To them, nudging the evolution of eyes or nervous systems might be no more exotic than gardening. To us, it would look like a miracle of natural selection. So far, when we sequence the DNA of living species and the fragments we can recover from ancient remains, we do not see obvious signs of tampering. What we do see are complex histories of duplication, mutation, and selection that tell a story of branching lineages. But remember, even our access to DNA is limited to relatively recent time. Molecules do not last forever. Beyond a certain age, the record shifts from genes to minerals. That is why some scientists describe the fossil record as a crime scene that has been rained on, burned, and buried under new construction for hundreds of millions of years. You can still pick out clues here and there, but the easy answers are gone. If someone did alter the course of evolution in the distant past, we would only be able to detect it through subtle statistical anomalies or patterns in how complexity arose and spread. There is another aspect to these sudden leaps that should give us pause. They are often accompanied by equally abrupt changes in the environment. When complex life spreads, we see shifts in the levels of oxygen and carbon compounds locked into rock. When forests take over continents, they change erosion, weather patterns, and the chemistry of the atmosphere. Life does not simply respond to the planet, it reshapes it. That feedback loop between life and environment is central to our own situation. Human industry is currently altering the air, oceans, and soil in ways that will be obvious in rock layers for a very long time. If another civilization had existed in deep time, its activities would have fed into that same loop. Even if its cities crumbled and its machines rusted away, the knock-on effects on climate and chemistry could persist. Imagine you are that future investigator again, drilling into Earth's crust and pulling out cores of ancient sediment. You would see sections where conditions change slowly, tracking cycles in the planet's orbit or long-term shifts in volcanic activity. Then you might find layers where things move much faster. Carbon levels jump, temperatures swing, extinction rates spike, and new species appear with novel traits. The challenge is deciding where to draw the line between nature and technology. For now, geologists lean heavily toward natural explanations, and for good reason. We have strong evidence that many major events were driven by things like huge volcanic provinces, asteroid impacts,
and continental rearrangements. The Silurian hypothesis does not claim that these interpretations are wrong. Instead, it asks us to add one more question to the list. Could an industrial civilization produce a pattern that looks so similar to natural events that we have been misclassifying it all along? That is not just a philosophical curiosity. It affects how we think about our own visibility in the cosmos. If planetary-scale civilizations can come and go without leaving unmistakable artificial signatures, then even a galaxy full of them might look empty from a distance. The famous question about where everybody is becomes sharper. Maybe the real issue is not that civilizations are rare, but that their traces blend into the background of planetary change. Keep that in mind as we move further into this deep-time investigation. The more we appreciate how messy, biased, and incomplete our record is, the more humble we have to be about making definitive statements. When we say we see no evidence of past technology, what we really mean is that we see no obvious artifacts that meet our current expectations. We are looking for metal in a world that may have learned to work with biology and fields instead. At the same time, this uncertainty gives us an unexpected opportunity. By asking what a hidden civilization would look like in the rocks, we sharpen our understanding of our own impact. We are forced to think in terms of markers that are durable, global, and distinct from short-term natural processes. That exercise can tell us not only how someone in the far future might detect us, but also how to spot ourselves in the present as a geologic event. There is a quiet but powerful comfort in that idea. It means we are not just passively reading Earth's history, we are actively rewriting it, and we have the tools to notice that rewriting as it happens. The same methods that revealed the asteroid impact that killed the dinosaurs can tell us where we sit on the spectrum, from ordinary climate cycle to something unprecedented. In the next step of this story, we are going to follow some of those markers more closely. Instead of looking only at fossils and their gaps, we will trace the path of certain elements and isotopes that act like signatures of technology. Natural processes can mimic some of those patterns, but not all. Nuclear reactions in particular leave ghostly fingerprints that persist for astonishing lengths of time. Before we go there, hold on to one simple picture. Life on Earth has not been a slow, steady climb up a ladder. It has been a sequence of long plateaus and sudden jumps, with many branches cut off along the way. Whether those jumps are purely natural or sometimes guided, they remind us that dramatic change is part of the planet's normal behaviour. Our own rapid transformation of the world is just the latest in that series. The real question, which will haunt the rest of this investigation, is whether we are living through a familiar pattern that has played out before, unseen, in earlier ages. When we start tracking nuclear ghosts through ancient rocks in the next part, the answer may begin to feel uncomfortably close. If you want to hide a civilization, you can strip away its buildings, grind its machines into dust, and let forests swallow its roads. But there is one thing that is almost impossible to erase. Once you split heavy atoms, the pieces they break into keep whispering about what happened for a very long time. Those whispers are what geologists sometimes call nuclear ghosts. They drift through rocks and minerals as unusual mixtures of isotopes, different flavours of the same element that behave like a forensic code. To understand how powerful that code can be, we can start with an event that nobody disputes. About 2 billion years ago, in what is now Gabon in West Africa, the planet itself built a nuclear reactor. Not a symbolic one, a real chain reaction where uranium atoms split, released energy, and produced a specific pattern of fission products that we can still see today. Back then, the proportion of the fissile isotope uranium-235 in natural uranium was higher than it is today. In a few places, uranium-rich ore bodies formed in porous rock, and groundwater flowed through them. Water slowed down stray neutrons just enough for them to trigger more fissions instead of flying harmlessly by. When conditions were right, the system turned on. It heated up, boiled away the water, and shut itself down. When it cooled, water returned, and the cycle started again. The result is what we now call the Oklo natural reactors, a set of ancient ore deposits where the isotopic makeup of the uranium is noticeably different from normal. There is less uranium-235 than you would expect from natural decay alone, and the surrounding rock contains specific concentrations of elements like neodymium and ruthenium that match the pattern of nuclear fission products. The chemistry is so distinctive that when it was first discovered in the 1970s, it briefly alarmed scientists, who wondered whether someone had been secretly enriching and burning fuel there. Once the natural explanation was understood, Oklo became a gift. It showed us exactly what a long-gone fission reactor looks like in the geological record. It proved that nuclear chain reactions can run in rock without any human help, and it gave us a baseline for what is possible without technology. If we ever stumbled across a different deposit with similar but not identical signatures, we would have something to compare it against. Hold that template in your mind, because it is the yardstick we will quietly use from here on. A technological reactor, one built by an industrial civilization, would also change isotopes in its fuel and host rock. It might concentrate certain rare elements, leak others, and leave behind a very specific profile of fission fragments and transuranic elements, those heavier than uranium. Some of those products decay quickly, but others persist for tens of millions of years. On top of reactors, there is another, even louder nuclear signal that modern humans have already sprayed across the planet. In the middle of the 20th century, we began testing nuclear weapons in the atmosphere and underground. Every detonation changed the ratio of carbon-14 in the air, sprinkled radioactive cesium and strontium onto soil and ice, and created traces of synthetic isotopes that simply did not exist in nature before. To geologists of the far future, those decades will show up as a razor-thin layer in sediments and ice cores where certain isotopes spike sharply and then fall away. It will be global, synchronous, and unmistakably artificial. No volcanic eruption or solar flare produces exactly that same combination. Even if all our cities disappear, that thin radioactive ring around the world will remain as a kind of timestamp, announcing that something capable of splitting atoms was active here. Now imagine that you are the investigator again, but you do not live in our time. You live tens of millions of years after us, sampling ancient rock for clues about planetary history. You have your own version of the Oklo template, and you understand natural fission. You know what background radiation looks like, how cosmic rays and spontaneous decays alter isotopes over eons. As you drill and measure, you expect a mostly smooth story, with occasional blips from lone phenomena. Then you encounter a sequence that does not quite fit. In one layer, the proportion of certain heavy isotopes jumps in a way that mirrors the pattern of deliberate fission. But the geometry of the deposit does not match a natural reactor. There is no clear ore body, no simple flow of water, no obvious mechanism for the reaction to sustain itself over long periods. Instead, the altered material is spread thinly across a wide area, as if dust had fallen from the sky. You move up and down through the rock and see smaller pulses above and below, echoing the same fingerprint in weaker form. It begins to look less like a single natural reactor and more like a series of discrete events. Energetic bursts, separated by thousands of years, each strong enough to change isotopes on a regional or global scale, then quiet again. If you mapped the intensity over time, it would resemble what human scientists now see when they chart our own nuclear weapons testing. A cluster of spikes fading away as treaties and politics changed behaviour. In our current reality, no such pre-human pattern has been confirmed. The anomalies that have been reported in deep time are debated and usually explained by known processes, like migration of elements through rock or the complex chemistry of ancient seas. That is important to keep clear, because we do not want to claim discoveries that have not been made. The point of the Silurian hypothesis is not to shout that there definitely were ancient wars, but to make us ask what they would look like if they had occurred. Once you start asking that question, it becomes natural to line up nuclear signatures with another set of puzzles we already study closely: mass extinctions. Earth's history contains several episodes when a surprisingly large fraction of species disappeared in a geologically short time. The end of the dinosaurs is just one example. There is the Permian event, sometimes called the Great Dying, where most marine and many terrestrial species vanished. There are lesser but still dramatic crises scattered throughout the record. Each of these events has its own chemical and physical traces. Some are linked to huge volcanic eruptions that coated continents in lava and flooded the air with carbon dioxide and sulfur gases. Some show signs of impacts, like the familiar iridium-rich clay and shocked minerals. Others involve rapid climate swings, ocean acidification, or loss of oxygen in deep waters. The standard toolkit of geology can account for much of what we see. Yet when you superimpose the idea of technology onto that canvas, a different layer of interpretation appears. Large-scale nuclear conflict, especially if extended over centuries, would release enormous amounts of energy into the atmosphere and oceans. It would produce characteristic fission products, but it would also trigger fires, smoke, and chemical reactions that could push climate and ecosystems past tipping points. Targeted weapons aimed at particular habitats or food webs could in principle produce extinctions that are surprisingly selective. Instead of a random culling across all groups, you might see specific branches of the tree of life cut away, while others pass through relatively unscathed. That pattern would mix with the more uniform effects of climate stress and habitat loss, creating a complex mosaic. When paleontologists look at actual extinction boundaries, they do sometimes find selectivity. Some groups are hit much harder than others. In many cases, this lines up with their biology. Species with narrow ecological niches, those that depend on specific foods or temperatures, tend to be more vulnerable when conditions shift. Highly mobile generalists often fare better. You do not need weapons to explain that. It is exactly what you expect from basic ecology under stress. Still, if you were searching for evidence of engineered extinctions, you would pay attention to cases where the selectivity is not easily explained by known environmental changes. You would look for the disappearance of organisms that pose particular obstacles to a rising civilization. For example, large predators, competitors for key resources, or species that stabilize climate in ways that prevent certain kinds of development. Alongside nuclear ghosts, there is another category of potential markers that might accompany technological warfare or industrial accidents: synthetic toxins. Modern humans have already created entire families of chemicals that did not exist on Earth before us. Some are designed to be stable and persistent, resisting breakdown in sunlight and water. If a civilization before us had similar habits, traces of their chemical inventions might still be locked in sediments. Organic molecules do degrade over time, but not all at the same rate. Some chlorinated compounds, fluorinated chains, and complex polymers can be surprisingly stubborn. In the deep future, their long, intricate carbon structures might survive as altered residues, distinguishable from natural organic matter by their unusual patterns. The exact details would depend on the chemistry, the environment, and the passage of time, but in principle, the idea is simple. Technology moves atoms into combinations that would rarely form on their own. Now step back and see how all these lines begin to intersect. A pulse of nuclear isotopes, a sudden selective extinction, a layer enriched in strange organic residues. Together, they could form a composite signature of a technological crisis, one where a civilization pushed its tools to the point of self-harm. In our own time, we can almost watch that pattern forming in real time as we spread plastics, industrial chemicals, and radioactive materials across the world. From the safety of the present, it is tempting to insist that any matching pattern in deep time would be impossible as anything but nature. Volcanism can mimic carbon spikes. Impacts can mimic sudden climate change. Natural reactors show that even fission can happen without intelligence. The Silurian hypothesis does not deny any of that. It simply points out that at some level of detail, the overlap is not perfect. Natural reactors like Oklo occur in specific geological settings. Their products are localized and tied to ore bodies. Volcanic provinces leave vast sheets of basalt and characteristic gas signatures. Impacts produce global debris layers, shocked minerals, and sometimes clearly identifiable craters. If we found a nuclear-like pattern smeared evenly across a planet, decoupled from ore and without the expected volcanic or impact features, we would be facing a harder question. Would we be ready to answer it honestly? Or would we stretch known processes to cover it because the alternative feels too strange? This is where the psychological component of the Silurian hypothesis quietly enters. We are not just dealing with data, but with our comfort level about what that data might imply. To admit the possibility of earlier civilizations is also to admit that our own story may not be unique, and that others have already faced the choices we are now making.
That realization is important, not only for understanding the past, but for reframing the present. If we think of ourselves as the first and only technological species, it is easy to treat our nuclear era as unprecedented, a one-off experiment in planetary scale risk. If we allow for the possibility that we are one in a series, then nuclear ghosts in the rocks become more than curiosities. They become warnings, traces of tests that did not end well. In that light, the work of tracking isotopes through deep time becomes a kind of conversation across millions of years. Natural reactors like Oklo speak of the planet's own experiments with fission. Our test ban era leaves a message for whoever comes next. Somewhere in between, there may be faint, ambiguous signatures that hint at stories we have not yet deciphered. As we follow those whispers, our focus naturally widens beyond reactors and bombs to the broader climate stage on which they play out. Nuclear events, whether natural or artificial, do not happen in isolation. They feed into long-term shifts in temperature, weather, and ocean circulation. If industrial ages have risen and fallen more than once, their lasting scars may be written more clearly in climate records than anywhere else. That is where we are heading next. We are going to lay human industrial emissions alongside ancient greenhouse spikes and ask how similar they really are. We will look at how long those signals linger after the factories go quiet, and what that means for seeing or missing a civilization in the deep past. Keep the image of those nuclear ghosts with you as we go, because in the story of climate, they may turn out to be only the first layer of a much larger pattern. When we talk about climate, it is easy to think of it as background scenery, the stage on which life and civilization perform their stories. In reality, climate is an active character. It responds to what life does, and in turn, it shapes what life can become. Every industrial chimney, every cleared forest, every engine that burns fuel is effectively a penstroke on that character. If any civilization had risen before us and mastered large-scale energy use, its choices would have been written into the same long diary of air and ocean that we are now editing. Right now, we can already see our own handwriting clearly. Since the start of the industrial era, the concentration of carbon dioxide in the atmosphere has climbed from roughly 280 parts per million to more than 400. That sounds like a small numerical change, but in physical terms it is enormous. It is enough to trap significantly more heat, shift weather patterns, melt ice, and raise sea levels. It is also fast. On geological timescales, what we are doing is like flicking a switch rather than turning a slow dial. Geologists have a name for events where carbon levels and temperatures spike abruptly. They call them hyperthermals. One famous example is the Paleocene-Eocene thermal maximum, a mouthful that describes a period about 56 million years ago when global temperatures jumped by several degrees in a relatively short span of time. In rocks from that interval, scientists find a sharp negative excursion in the ratio of carbon isotopes, a sign that a large amount of lighter carbon flooded the system. The standard explanations involve massive releases of methane from the seafloor, burning of organic-rich sediments, or the outgassing of volcanoes. All are plausible, and each has some supporting evidence. What matters for our story is the shape of the signal. In the Paleocene-Eocene event, carbon climbs quickly, stays high for tens of thousands of years, then slowly declines as the planet's natural feedbacks pull it back down. Temperatures follow a similar path. When we overlay our modern carbon curve onto that ancient one, the resemblance is unsettling. Ours is steeper so far, and more tightly tied to fossil fuel burning, but the outline is similar. If you were the distant investigator reading both events in core samples with no other context, you might see them as members of the same family: rapid carbon addition, warming, ocean acidification, disruption of ecosystems, then gradual recovery. For a natural event,
The carbon comes from reservoirs like methane hydrates or peat and coal seams ignited by lava. For an industrial event, the carbon comes from the deliberate burning of coal, oil and gas. To the rocks, the difference is mostly in the fine detail. That fine detail is where the Silurian hypothesis asks us to look more carefully. Industrial emissions have characteristic fingerprints. For example, fossil fuel carbon is depleted in carbon-14 because it has been locked away for millions of years, allowing that isotope to decay. When we burn it, we dilute the atmospheric carbon-14 signal. That is something a future geochemist could detect. Industrial processes also release specific combinations of nitrogen compounds, sulfur oxides, and trace metals that natural sources rarely match exactly. On top of greenhouse gases, modern societies emit aerosols, tiny particles that float in the air and influence how much sunlight reaches the surface. These can be soot, sulfate droplets from burning high-sulfur fuels, or dust from agriculture and construction. In recent decades, scientists have noticed that some of these particles actually cool the planet by reflecting sunlight, partly masking the full warming effect of greenhouse gases. We did not plan it that way, but the outcome resembles a crude form of climate engineering. Now imagine a civilization that does this on purpose, and with far more sophistication. If they understood climate physics deeply, they could design specific aerosol mixtures to fine-tune regional temperatures, stabilize monsoons, or prevent polar ice from melting. They might even spread these aerosols from aircraft or high-altitude platforms in targeted patterns. Over time, some of those compounds would settle into snow and sediments, preserving a record of their experiments. Some of the substances we use today for industry and refrigeration, such as chlorofluorocarbons, are entirely synthetic. They have no natural sources. In ice cores from the last century, their concentrations rise from 0 to detectable levels, then fall again as regulations take effect. For a future investigator, those molecules would be a smoking gun of technology. They would be a clear sign that someone was manufacturing complex chemistry and releasing it into the sky on a global scale. If a prior civilization had its own synthetic climate-active compounds, the same logic applies. The exact molecules would be different, tailored to their materials and engineering preferences. After millions of years, those compounds would break down, but not all breakdown products are boring. Some leave behind unusual halogen-rich or metal-rich residues that could, in principle, still be recognized as out of place. There is another angle that often gets less attention. Industrial activity does not only push carbon dioxide up. Over long periods, it can also pull it down. If a civilization became serious about managing its climate, it could plant enormous forests, cultivate plankton blooms in the ocean, or build machines that actively capture carbon from the air and bury it. If they succeeded, the geological record might show not just a spike, but a spike followed by an overcorrection, where carbon levels drop below their previous baseline. That kind of pattern is unusual in purely natural events. Feedbacks like weathering and ocean uptake are strong, but they tend to bring the system back toward balance, not beyond it. When you see sharp reversals, it is often because the driving force itself has changed sign. Something that was a source becomes a sink. For us, that kind of engineered reversal is still mostly a dream. For a much older civilization, it might have been business as usual. Then there is oxygen. The amount of free oxygen in the atmosphere has not been constant over Earth's history. It rose dramatically during the Great Oxygenation event billions of years ago, when photosynthetic microbes flooded the air with this reactive gas. It has fluctuated since, sometimes dropping low enough to limit large animal life, sometimes climbing higher than today. Those changes are recorded in rocks, through things like the oxidation state of iron and sulfur minerals. A civilization that relies on combustion, like ours, tends to consume oxygen faster than it creates it. But one that harnesses photosynthesis at scale, perhaps through global networks of engineered organisms designed to maximize energy capture, could intentionally raise oxygen levels to support high metabolism and dense populations. That would change fire regimes, the efficiency of respiration, and the chemistry of the upper atmosphere. To a geologist, it would look like a sharp staircase rather than a gentle slope. Now consider the possibility of deliberate temperature stabilization. We already discuss ideas like that under the label of geoengineering. Proposals range from placing reflective particles in the stratosphere to brightening marine clouds or adjusting land surface properties. Most of these would leave distinctive regional patterns in temperature and precipitation, but might not show up neatly in a single global average. If a civilization applied them for thousands of years, trying different strategies, the result could be a patchwork of signatures. In lake sediments, you might see repeated cycles where the local climate tries to drift one way under natural forcings, only to be nudged back abruptly. Tree rings could show alternating periods of stress and relief that do not line up with known volcanic eruptions or solar variations. Ice cores might record oscillations in dust and aerosol types that do not match typical desert or wildfire sources. Each anomaly by itself could be dismissed as noise. Together, they could hint at a guiding hand. Of course, all of this remains extremely speculative. The current scientific consensus is that the known ancient climate spikes can be explained without invoking lost civilizations. Gigantic volcanic provinces like the Siberian traps can spew enough carbon and sulfur into the atmosphere to warm the world and acidify the oceans for hundreds of thousands of years. Changes in the shape of Earth's orbit can modulate sunlight and trigger ice ages and warm periods. Carbon reservoirs beneath the sea can destabilize and burp their contents in relatively sudden bursts. The Silurian hypothesis does not deny these mechanisms. It simply asks us to treat them as part of a broader menu of possibilities rather than the only game in town. When we study an ancient hypothermal, we can ask not only whether volcanoes and methane can account for the observations, but also whether the pattern matches what we would expect from a short, intense industrial era. The answer might be no every time, or it might be a cautious maybe, where data and models leave room for multiple interpretations. There is a subtle but important benefit to thinking this way. By viewing our own industrial age through the same lens we apply to ancient events, we gain a more realistic sense of how visible we will be in deep time. We can calculate how much carbon we are adding, how long it will take for weathering and ocean uptake to erase most of it, and what fraction will remain locked in carbonate rock or organic matter. We can estimate which synthetic compounds might survive as altered residues, and how thick our aerosol layers will be in future sediments. When researchers do those exercises, they find that some parts of our impact will fade within tens of thousands of years, while others could linger for millions. The signal is not as strong as the most extreme volcanic episodes, but it is not trivial. It would stand out to a careful investigator. That means that if someone had done something similar tens of millions of years before us, there is at least a chance that we could see it, especially if we know what to look for. And yet, when we examine known climate events, we do not find anything that screams obvious technological origin. We do not see clean, sharp transitions that reverse neatly on human timescales. We do not see synthetic molecules that resist all known natural pathways. Instead, we see messy, drawn-out stories that fit reasonably well with natural drivers. The rocks are not shouting about ancient factories. If there was a civilization before us, either it behaved very differently from ours, or its climate experiments are mixed so deeply into natural cycles that they are effectively invisible. There is one more twist that complicates things further. Technology does not have to be purely destructive. A sufficiently advanced civilization might design its entire energy and agriculture system to minimize waste and avoid large climate disruptions. Instead of burning stored carbon, it could harvest sunlight with near-perfect efficiency, tap geothermal gradients, or use nuclear fusion cleanly. In that case, its biggest mark on climate might be subtle, like slightly reduced temperature gradients between equator and poles due to waste heat, or tiny anomalies in atmospheric composition from trace byproducts. From our perspective, such a civilization would be nearly silent in the geological record. It would have infrastructure, culture, perhaps even spaceflight, yet leave behind only faint whispers in the climate data. The absence of a loud, obvious signal in ancient rocks would not prove they never existed. It would only tell us that if they did, they were wiser or quieter than we are, at least in how they treated their atmosphere. All of this brings us back to a simple, humbling idea. Climate is both archive and amplifier. It remembers what life does and it magnifies the consequences.
Whether driven by volcanoes, orbital cycles, or industry, shifts in greenhouse gases and aerosols ripple through ecosystems and leave lasting scars. Our own industrial age is now one of those scars in the making. The hypothermal we are engineering will, in time, sit next to events like the Paleocene-Eocene spike as another chapter in the book. If that book already contains chapters written by earlier technological species, we have not yet learned how to read them with confidence. But even the attempt to look changes us. It forces us to see ourselves not as a special exception, but as a test case. Are we heading toward the same kind of abrupt transition that has ended worlds before? Or are we starting to bend the curve in a new direction? To answer that, we have to expand our search beyond air and ice, and into places where physical infrastructure might survive in unexpected forms.
The deep ocean floor, shielded from many surface processes, is one of the best candidates. In those dark, high-pressure realms, clues to lost industrial ages might be waiting in the shape of the seafloor itself. In the next stage of this investigation, we will dive down to those trenches and ridges and ask whether their patterns are entirely natural or whether some of them look suspiciously like the footprints of machines. If you want to hide something on Earth for a very long time, the deep ocean is one of the best places to try. Sunlight never reaches the abyssal plains. Temperatures are just above freezing. The water is dense, still, and heavy. Storms on the surface barely matter. From the point of view of geology, it is a quiet vault where sediment drifts down like slow snow and buries whatever lies beneath. If any civilization wanted its infrastructure to fade from sight but not from existence, the seafloor would be a tempting canvas. We know this in a small way from our own behaviour. Today there are thousands of kilometres of fibre optic cables stretched along the bottom of the oceans, linking continents with glass threads as thin as a finger. There are pipelines carrying oil and gas, and experimental sites for deep-sea mining. From the surface, you cannot see any of it. On a sonar map, though, these structures appear as thin lines, gentle trenches, and small geometric patches that do not quite match the rough randomness of natural terrain. Sonar is our main tool for mapping the seafloor. Ships send out sound pulses and measure the echoes. Over decades, as survey vessels cross and recross the oceans, their tracks accumulate in datasets that scientists can turn into relief maps. At low resolution, the big features stand out clearly. You see mid-ocean ridges, deep trenches, fracture zones, and large seamounts. At higher resolution, you begin to notice smaller patterns, including the straight paths of the survey ships themselves. That last point is important, because our brains are excellent at seeing order even where none exists. Early maps sometimes gave the illusion of grid patterns across the ocean floor, just because of the way shipping lanes overlapped and the data was processed. In reality, plate tectonics produces long, parallel ridges and faults, not perfect checkerboards. If we want to look for truly unnatural geometry on the seafloor, we have to be careful not to confuse artifacts of measurement with artifacts of engineering. Imagine for a moment that you could strip away that confusion and see the true underlying shapes. What would an industrial footprint in the deep ocean look like after millions of years? Large-scale mining would remove or disturb layers of mineral-rich nodules, especially the manganese nodules that dot many abyssal plains. Instead of a uniform sprinkling, you might see wide swathes where nodules are missing or broken, with sharp edges gradually smoothed by slow growth and sediment. Tunnels or caverns carved into harder rock could collapse and be filled, leaving subtle depressions or unusual rubble. If advanced machines had tapped hydrothermal vents for energy, they might have altered the chemistry of the fluids, stripping out certain metals or compounds preferentially. Later, when natural vent activity resumed or shifted, the mineral chimneys that grew could carry a strange legacy, a gap or skew in their elemental recipes that does not match nearby regions. To a geochemist, those anomalies would look like someone had filtered the vent fluid with a hidden refinery. We can get a sense of these possibilities by looking at how our planned deep-sea mining would appear to future investigators. Proposals often involve large robotic vehicles that scrape the top layer of sediment and collect nodules, stirring up thick plumes of silt that drift for many kilometers before settling. That process will leave behind smoothed tracks, altered nodule fields, and thin layers of disturbed sediment that differ in grain size and composition from the layers above and below. In a few million years, erosion and new deposits will blur the sharp edges, but the overall pattern could survive. All of this relies on the fact that the ocean crust itself is not eternal. New seafloor is continuously created at mid-ocean ridges and destroyed where plates dive back into the mantle. The average age of the ocean floor is on the order of 100 million years or less. That means any infrastructure older than that has been swallowed, melted, and recycled. If a civilization achieved its peak more than a couple of 100 million years ago, almost all direct physical traces on the deep seafloor would now be gone. On the other hand, if it flourished within that window, there is at least a chance that some clues remain in younger basins, especially in regions where subduction is slow or absent. Abyssal plains, with their gentle slopes and steady rain of fine particles, are particularly promising. They act like blank sheets on which any disturbance stands out. Even if buildings and machines collapsed, their denser components could be preserved in the sediment as scattered metallic fragments, ceramics, or glass-like materials. The challenge is that we have only mapped a fraction of the ocean floor in high detail and sampled an even smaller fraction with cores and submersible dives. Most of what we know comes from broad surveys designed to answer large-scale questions about plate tectonics and marine geology, not to hunt for grid patterns or buried alloys. That leaves plenty of room for imagination, and also a clear path for more focused research. If you wanted to seriously test the Silurian hypothesis in the oceans, you would target specific regions and look for combinations of geometric forms, unusual material concentrations, and altered mineral deposits. Now lift your eyes off the seafloor and think about why a civilization might favour the deep ocean in the first place. It offers privacy, stability, and a measure of protection from impacts and surface disasters. It is also rich in raw materials and energy gradients. Hydrothermal vents, cold seeps, and strong currents all present opportunities for power generation. In science fiction, visionaries imagine entire underwater cities and factories hidden beneath thermoclines, drawing power from the Earth itself. If any real society ever did that, the ocean would be both its shield and its tomb. Even if Earth eventually erased most of that activity, the story might not end there. A civilization capable of industrializing the oceans would almost certainly also reach into space. It would have reason to build launch platforms, set up refueling sites, and exploit resources beyond its home planet. That brings us to perhaps the most durable record of all, not on Earth, but on the relatively unchanging surfaces of nearby worlds. The Moon is a prime example. It has no thick atmosphere, no liquid water, and far less tectonic activity than Earth. Craters from the earliest history of the solar system are still visible. Footprints from the Apollo missions will remain for millions of years unless disturbed by micrometeorites. Any large-scale mining or construction done on the Moon in a previous age would have an excellent chance of leaving recognizable scars. What would those scars look like? Open pit mines would appear as sharp-edged depressions with unnatural shapes, perhaps nested terraces rather than smooth, bowl-like forms. Waste rock and slag could form mounds with distinct reflectivity and composition compared to surrounding regolith. Transport networks might carve straight or gently curving trenches between sites, inconsistent with typical impact features. Energy facilities could be associated with arrays of reflective surfaces, though these would slowly degrade under constant radiation and tiny impacts. Modern lunar orbiters already give us detailed images of much of the surface. So far, they show plenty of intriguing geology, but nothing that clearly screams engineered megastructure. The same holds for the mysterious far side. It is rougher and more heavily cratered than the side that faces Earth, but its features line up well with natural processes. That does not absolutely rule out past activity. Smaller installations could be buried by dust, or located in regions we have not yet imaged at the highest resolution. Still, the absence of obvious anomalies is a sobering data point. Mars presents a similar mix of promise and disappointment. With its thin atmosphere, extinct volcanoes, dried riverbeds, and layered sedimentary rocks, it looks like a place that once had conditions friendly to life. If a civilization based on Mars or visiting it from elsewhere had tried to terraform it, we might expect to see unusual mineral ratios, altered patterns of erosion, or chemical leftovers in the soil. Early telescopic observers imagined straight lines across Mars and called them canals, but modern spacecraft have resolved those illusions into natural valleys, ridges, and streaks shaped by wind and dust. If someone had truly reworked the Martian climate, the most durable signature might be in the isotopic composition of its atmosphere and polar caps. Large-scale industry and deliberate gas releases or removals could shift the balance of light and heavy isotopes of elements like carbon, oxygen, and nitrogen. Some of those imprints would persist, even as the atmosphere thinned or thickened again. Scientists are already using this kind of analysis to infer the loss of Martian air to space. To date, nothing requires technological intervention as an explanation. Nature appears messy but sufficient. Even above the surfaces of these worlds, there is room for a story. Any spacefaring society will create orbital debris, intentionally or not. Satellites age, rockets leave spent stages, collisions generate clouds of fragments. Around Earth today, there is already a belt of artificial objects that future astronomers could detect by their reflectivity and motion. Over time, atmospheric drag will pull most of that material down, where it will burn and sprinkle tiny droplets of metal into the upper air. If a civilization maintained a high level of space activity for millions of years, its orbital zones would continuously shed debris onto nearby surfaces. The Moon, with no atmosphere to remove it, would collect a slow rain of impactors made of refined alloys, composite materials, and other engineered substances. Over long timescales, those fragments would be ground into dust and mixed into the regolith. A careful survey could still reveal an anomalous concentration of certain alloy combinations that are hard to produce through natural meteoritic processes. Asteroids and small moons add another layer. They are rich in metals and volatiles and are attractive targets for mining. Cutting and hauling away material would change their shapes, spin rates, and internal structure. Large cavities hollowed out and then abandoned might eventually collapse, leaving oddly geometric basins. Natural collisions can also do this, so once again the difference would be in the statistical patterns and the chemical footprints of processed versus raw rock. This is a lot of speculation, but it serves a practical purpose. It forces us to inventory where we ourselves are leaving durable marks. We are altering the seafloor, yes, but we are also installing artifacts on the Moon, Mars, and several asteroids. We are building a halo of debris around our planet that will gradually be written into other bodies. Even if Earth's crust completely recycles our cities, the broader solar system will carry a fossil record of our technological phase long after. Seen through that lens, the question of earlier civilizations becomes less abstract. If someone had reached our current level and then continued for millions of years, we would expect the Moon and nearby objects to look different from what we see. Their surfaces would carry long histories of excavation and construction. The fact that they appear mostly untouched suggests either that such a civilization never arose here before, or that it used methods and materials that blend indistinguishably with natural geology, or that it did not choose to leave its home system in obvious ways. There is one more possibility that brings us back down from rock and metal to something stranger. Maybe the most advanced civilizations do not rely on large physical structures at all, at least not in the way we imagine. Instead of building towering factories and sprawling cities, they might embed their capabilities into life itself, or into the fine structure of minerals. They might turn the biosphere and the crust into a distributed machine, leaving very little that looks like a separate technological layer. We have already taken the first small steps in that direction with genetic engineering and with ideas about storing data in DNA. Researchers have also learned to encode information in crystal defects and layered materials. Compared to building a rocket, these tricks seem subtle. Compared to writing your presence into the entire fabric of an ecosystem or a planet, they are almost trivial. If someone had mastered that path long ago, the real record of their existence would not lie in seafloor grids or lunar quarries, but in patterns of genes and crystal lattices that we have only begun to notice. In the next stage of this journey, we will follow that lead. We will stop looking for skyscrapers turned to dust and start asking whether life itself and the rocks it grows upon could have been used as hardware for a planetary-scale information system. If that sounds far-fetched, Remember that every cell in your body already carries a coded record of billions of years of evolution. The line between natural archive and deliberate computation may be thinner than it appears. When we picture advanced technology, we tend to see shiny devices and glowing screens, not forests, microbes, and crystals. Yet every cell on this planet already holds a molecular archive that puts our data centers to shame. DNA is a compact, self-copying, self-repairing storage system that has carried information across billions of years. Long before we etched bits into silicon, Earth was writing and reading instructions in sequences of 4 chemical letters. If you wanted to build something that could last through ice ages, asteroid strikes, and shifting continents, you could do a lot worse than using life itself as your hardware. We know this not only in theory, but from our own experiments. In the last decade, researchers have encoded books, images, and even entire operating systems into synthetic strands of DNA and then read them back with high accuracy. They did this as a demonstration, a proof that genetic molecules can store arbitrary information, not just the blueprints for cells. It worked because the underlying machinery is already there. Cells know how to copy and protect DNA. All we did was hijack that capacity. Once you see living tissue as a potential information medium, an unsettling question arises. What if someone else realized this long before us and took it much further? Instead of building separate machines, they might have woven their computation and memory directly into the genomes of organisms and the structure of ecosystems. In that scenario, the difference between an ordinary forest and a piece of planetary infrastructure would not be visible from space. It would live in the patterns of genes and interactions. To evaluate that idea, we can start from what we already know about evolution. Genomes are messy. They carry the fossils of ancient viruses, duplicated segments, and long stretches of sequence that seem to do nothing obvious. Genes move not only vertically, from parent to offspring, but also horizontally between species, through mechanisms like viral infection and symbiosis. Across billions of years, this has created a tangled web of shared modules and repurposed functions. From one angle, that tangle already looks like code reuse in software. The same core genetic motifs appear in distantly related organisms, adapted for different roles. Natural selection explains that very well. Useful solutions tend to be conserved. But if you were also open to the idea of deliberate design, this is exactly the kind of structure you would expect from engineers who prefer to reuse and recombine reliable components rather than reinvent everything from scratch. The challenge is separating those two interpretations. At our current level of understanding, the evidence points strongly toward natural processes. The statistical patterns of mutation, selection, and drift fit models that do not require an external programmer. Yet the Silurian hypothesis invites us to ask a more subtle question. Are there features in the tree of life that would be extremely unlikely under purely natural evolution, but easier to explain if someone had, at some point, nudged genomes in coordinated ways? One candidate is highly synchronized change across many unrelated lineages. If, over a relatively short interval, a wide range of species acquired similar beneficial traits with nearly identical genetic implementations, that might hint at common intervention. There are cases in evolution where similar solutions arise independently, such as different animals evolving camera-like eyes or streamlined bodies in water. These convergences often use different underlying genes or developmental pathways. Engineered convergence would look tighter, as if the same patch had been applied everywhere. Another clue might be the presence of information that has no obvious biological function. Imagine discovering long segments of DNA that encode structured data, mathematical objects, or patterns only recognizable to a sophisticated decoder, yet are conserved across species and time. We have not found anything like that. Most of the so-called non-coding genome either plays subtle regulatory roles or behaves like neutral baggage. But if an earlier civilization embedded messages or algorithms in DNA, we would need the right mathematical lenses to even notice. This is where our own work in fields like artificial life and evolutionary computation becomes relevant. We already use digital genomes and selection pressures to evolve solutions to engineering problems. In some experiments, Systems of interacting agents develop strategies and behaviors that even their designers did not fully anticipate. That is a hint that life, whether natural or guided, is capable of exploring vast spaces of possibility and storing sophisticated adaptive knowledge in its genetic material. Now extend that idea from individual organisms to entire ecosystems. Forests, coral reefs, and soil communities are not just collections of separate species, they are networks of exchange and feedback. Trees communicate nutrient needs through fungal threads. Microbes sense and respond to chemical gradients across tiny distances. Animals spread seeds and microbes as they move. You can think of these networks as enormous, slow, parallel computers, constantly integrating information about climate, chemistry, and energy flow, and adjusting their structure accordingly. If a civilization understood that deeply, it could design interventions that harness those networks rather than fighting them. It might create organisms whose main purpose is to coordinate information, not to compete for resources. It might tune microbial communities so that they collectively regulate climate variables or detect and correct disturbances. From the outside, this would look like a remarkably stable, resilient biosphere. From the inside, it would be more like a living operating system. We can already glimpse very small versions of this in our own attempts to restore ecosystems or manage agriculture. Engineers talk about using biological circuits, microbial consortia, and engineered symbioses to maintain soil health and crop yields with less external input. These are crude first steps compared to what a truly advanced biosphere technology would look like. Still, they show the general direction, using life as hardware and software at once. So far, nothing in the fossil or genetic record forces us to conclude that such deliberate biosphere engineering has occurred, but asking how it might manifest gives us new tools. We can look for periods in Earth's history where ecosystems recover from shocks faster than models predict, or where climate stability persists under conditions that should have produced wild swings. We can search for unusual alignments between genetic change and environmental shifts, as if adaptation were not merely reactive, but anticipatory. Beyond life, there is the mineral world. Crystals seem like the opposite of living tissue. They are rigid, regular, and inert. Yet at a physical level, they can store information too. In a magnetic material, the orientation of tiny domains can encode bits. In some oxides and semiconductors, patterns of defects and impurities control how current flows, effectively shaping the material into a computation device. Every hard drive we use exploits this principle. Every microchip relies on precise arrangements of dopants in a crystal lattice. Earth is full of such lattices. Deep in the crust and mantle, pressures and temperatures shape minerals into complex structures with layers, defects, and grain boundaries. Fluids percolate through them, changing their chemistry. If you wanted a medium that could hold patterns for geologic time, you could do worse than a well-chosen mineral phase, buried far from weather and erosion. Encode information in the position of impurities or the orientation of domains, and it might sit there quietly for hundreds of millions of years. We already know that crystals record aspects of their environment. Growth bands in some minerals reflect changes in temperature and composition of surrounding fluids. Zircon grains carry isotopic clues about the age and conditions of their formation. It is not a stretch to see these as a kind of natural logging system. The Silurian hypothesis nudges us one step further and asks whether such systems could be repurposed into intentional storage, dense with structured information, rather than mere environmental snapshots. Imagining how that would work is an exercise in applied creativity. You might take a host mineral that forms extensive veins or layers, then carefully control its growth so that impurities align in a binary pattern. That pattern could be encoded at scales far too small to see with the naked eye, but accessible with the right spectroscopy. You might distribute these information-rich veins globally, so that even after plate motions, fragments remain on every continent. To a geologist unaware of the code, it would look like ordinary ore. To someone in on the secret, it would be a library. Now connect these mineral archives back to the biosphere. A civilization that uses both could design organisms that seek out particular minerals, read or write information using biochemical tools, and then carry that information elsewhere. Microbes already dissolve and precipitate minerals as part of their metabolism. They already sense and respond to subtle chemical gradients. It is not hard to picture a living layer that interfaces with a crystalline layer, forming a tightly coupled biological-geologic computer. At that point, the entire planet begins to look like a single device. Energy from the sun and the interior drives flows of heat and matter. Life captures a fraction of that flow and organizes it into chemical and genetic patterns. Minerals capture another fraction and organize it into structural patterns. Feedback loops connect the two. Over time, such a system could develop stable attractor states, configurations that it tends to return to even after disturbances. To an external observer, that would look like a planet that mysteriously maintains certain conditions, as if guided. Here again, we have to be clear about what is speculation and what is evidence. Earth does exhibit a surprising degree of long-term stability in some parameters, like the presence of liquid water and moderate temperatures over billions of years. Some scientists explain this through the Gaia hypothesis, the idea that life and environment co-evolve in ways that promote continued habitability. In most versions, this is an emergent property, not a conscious design. The alternative reading would be that at some point, evolution crossed a threshold where the biosphere became self-aware in a functional sense and began to deliberately steer itself. If that sounds mystical, remember that self-regulating systems do not need a central mind in the way we usually imagine it. Your own body maintains temperature, blood chemistry, and countless other variables without any conscious effort on your part. Networks of cells and hormones do the job. A planetary-scale network of organisms, minerals, and fields could, in principle, do something similar. The question is whether that ever happened, and whether signs of such control would be distinguishable from ordinary feedbacks. One promising route is to study fine-grained anomalies in the timing and magnitude of environmental changes. For example, if carbon dioxide levels in the past consistently bounced back from perturbations faster than models based on known natural feedbacks would allow, that might hint at hidden regulation. If certain dangerous configurations, like complete glaciation or runaway greenhouse states, were systematically avoided even when external conditions might have favoured them, that too would be suggestive. Not conclusive, but suggestive. Now imagine that a technological civilization grew out of such a self-steering biosphere. At first it might look like us, with separate tools and infrastructures. Over time, as it matured, it might progressively dissolve the boundary between technology and nature. Instead of factories, it would cultivate highly efficient metabolic networks. Instead of computers in boxes, it would use distributed biochemical and crystalline processes. Instead of cities as we know them, it might favour living structures that grow and heal. What would be left of that civilization after deep time had done its work? You would not find skyscrapers or cars. You might not even find obvious mines or waste dumps. You would, however, inherit a biosphere whose genetic and ecological architecture had been tuned for performance and resilience, and a crust whose mineral patterns carry dense correlations that look oddly intentional. To notice that, you would need tools and theories far beyond what we currently have. There is a quiet twist here that loops back to our own position. We are just beginning to acquire the ability to read genomes at scale and to map subtle variations in crystal structure. As those tools improve, we will almost certainly find surprising regularities and patterns. Most of them will have natural explanations, some may not. The mindset we bring to that analysis will matter. If we assume from the outset that intelligence can only appear in forms we recognize, we may overlook more integrated and subtle expressions of it. Even if we never find a single convincing sign of prior engineering, thinking this way has value. It nudges us toward technologies that are more blended with the living world and less dependent on fragile external infrastructure. It suggests that the most robust long-term way to compute, store, and regulate might be to work with the grain of biology and geology, instead of against it. In a sense, the Silurian hypothesis becomes less about ghosts and more about blueprints for a sustainable future. Because once you understand how a planet itself can act as a computer, another possibility opens up. Information processing need not be confined to molecules and crystals. It can also live in fields, in the shape of electromagnetic and gravitational structures that span entire regions of space. If any civilization learned to encode memory and control directly into those fields, its infrastructure would be almost impossible to see with ordinary senses. Yet its influence on orbits, radiation belts, and particle flows could be very real. That is where we are heading next. We are going to take the idea of a living computing Earth and extend it outward into the space around our planet and across the solar system. We will ask whether some of the subtle anomalies in particle streams and asteroid paths could be the byproducts of a protective architecture built long before us. In other words, we will move from rock and life as hardware to the possibility that the space between worlds has been quietly programmed as well. So far, we have treated the hardware of lost civilizations as something you might touch, even if only in imagination. Rocks, genomes, minerals, and oceans. But information does not have to live only in matter. It can also live in patterns of energy and fields, woven into the invisible scaffolding that surrounds a planet. Once you step into that territory, the idea of a civilization leaving almost no solid relics becomes less absurd. Its most important infrastructure could be built out of shapes in space and time. You already live inside one such structure, whether you think about it or not. Earth's magnetic field reaches far into space, forming a protective bubble that deflects charged particles from the sun. Within that bubble, electrons and ions spiral along field lines, trapped in belts. Currents flow along the boundary where the solar wind pushes and the magnetosphere pushes back. None of this is designed in the usual sense. It arises from molten metal moving in Earth's core and from plasma physics. Yet the outcome is almost tailor-made to shield a fragile biosphere from radiation. Now imagine a civilization that understands those field interactions in exquisite detail and can manipulate them deliberately. We already nudge the magnetosphere in small ways with our radio transmissions, power grids, and experiments that inject charged particles. Scale that idea up by factors of millions, and you can begin to picture a system that uses the planet's natural field as a backbone for computation, communication, and protection. Instead of building towers and cables, it shapes currents in plasma and modulates waves in space. The physics is not mystical. Plasmas are responsive. Change the electric or magnetic environment, and particles reorganize. In the laboratory, scientists have created complex wave structures and self-organizing patterns in dusty plasmas. In space, the sun and planets constantly send and receive disturbances along invisible field lines. A sufficiently advanced civilization could tap into those flows the way we tap into rivers and wind. Its circuits would be streams of charged particles. Its memory could be stored in the configuration of entire regions of the magnetosphere. What would that look like to us? Mostly like noise. Our instruments would register variations in particle fluxes and fields that we would chalk up to solar storms and natural turbulence. Only with very careful analysis might we notice that some patterns are too persistent or too finely tuned to be random. Maybe certain resonances recur with uncanny regularity, as if some part of the system is humming on purpose. Maybe field lines reconnect in ways that optimize energy transfer to specific latitudes, subtly stabilizing climate or steering storms. We are nowhere near that level of control, but we have already seen hints of how delicate the balance is. Large solar flares can compress the magnetosphere and induce currents in long conductors on the ground, sometimes knocking out power grids. That means our technological layer is already coupled to the planet's space environment. Turn that relationship around and ask what would happen if the coupling were guided from the other side, from the space environment inward. A system designed to dampen dangerous currents could prevent blackouts. One designed to enhance certain frequencies could drive communication without conventional transmitters. There is another set of fields that may be even more fundamental, gravitational ones. Every mass in the solar system curves space-time. Orbits are the visible traces of that curvature. We tend to think of gravity as too weak to control without astronomical amounts of energy, which is true with our current tools. But if a civilization had access to technologies that manipulate mass distribution or exploit quantum effects in gravity, it could in principle nudge trajectories of asteroids, comets, and even planets over long timescales. Oddly enough, that is exactly the kind of quiet influence you would want if your goal were to protect a biosphere from catastrophic impacts. Instead of building shields or destroying incoming objects at the last minute, you could adjust their paths centuries or millennia in advance so that they miss your world entirely. Tiny changes in velocity, applied early, compound over time into large deflections. The energy cost, spread out, could be far lower than brute force methods. From our current vantage point, it is hard to tell whether any such long-term choreography has ever happened. The distribution of asteroids and comets today mostly fits what we expect from gravitational dynamics and collisional history. Still, there are curious details. Some near-Earth asteroids have orbits that bring them startlingly close to our planet, yet never quite cross certain danger thresholds. Over long intervals, resonances with planets can trap objects in stable configurations. That is all explainable through known mechanics, but if someone were quietly adjusting things within the limits of that mechanics, their work might be nearly indistinguishable from a universe that simply got lucky. This is where we bump up against a deeper philosophical tension. How do you distinguish between a system that is naturally self-stabilizing and one that is being gently guided? Your body temperature stays within a narrow range because of evolved feedback loops. If some external caretaker occasionally nudged those loops behind the scenes, you would have a hard time noticing. On planetary scales, feedbacks like the carbon cycle and ice albedo effects already provide some degree of self-regulation. Adding a layer of intelligent control on top could look, from a distance, like unusually effective natural resilience. Consider Earth's magnetic field again. It has reversed polarity many times, and its strength waxes and wanes. During low-strength periods, more cosmic rays and solar particles can reach the atmosphere and surface. Some models suggest this could influence climate or mutation rates. A civilization that depends on a stable environment might find those swings inconvenient. If it could reinforce the field when it weakens, perhaps by driving currents in the outer core or in the surrounding plasma, it could smooth out the most dangerous dips. Would that leave a detectable signature? Possibly, if the timing of field strength changes systematically avoided certain configurations that physics would otherwise permit. We have paleomagnetic records from rocks and sediments that show how the field has behaved over tens of millions of years. They reveal a complex pattern of reversals and excursions. So far, nothing in that pattern demands an intelligent explanation. Still, it is the sort of data set you would examine if you wanted to check for hidden guardianship. Now move further out, to special places in the solar system where gravity balances out in elegant ways. These are the so-called Lagrange points, positions where the gravitational pull of two bodies and the centrifugal effect of orbit line up. Around Earth and Sun, there are 5 such points. Around Earth and Moon, there are 5 more. They are prime real estate for observers, relay stations, and platforms that need a stable view. Modern agencies already place solar monitoring satellites at the sunward Lagrange point and plan telescopes and habitats for others. A civilization that wanted to monitor and subtly manage a planet over very long times would likely use these same vantage points. From there, it could watch incoming comets, track flare activity on the star, and coordinate any interventions with minimal delay. That intervention might be as mundane as firing small deflection pulses at dangerous objects, or as exotic as modulating fields that couple back to the planet's interior. Structurally, these guardians could range from physical constructs to pure field configurations, depending on the available technology. So far, surveys of our own Lagrange points have not revealed vast structures or obvious machines. We see dust, occasional asteroids, and a handful of human artifacts. At the same time, our searches are far from complete. Many small bodies and potential artificial objects could lurk unseen, especially if they are designed to be dark and non-reflective. More intriguingly, if the main action lives in fields rather than hardware, there may be nothing solid to see at all, only subtle anomalies in particle flows and wave propagation. You might be wondering at this point whether we are simply importing magic back into a story that began as a rigorous thought experiment. It is a fair concern. The Silurian hypothesis is only useful if it stays grounded in testable questions. That is why the right way to think about invisible guardians is not as mythic beings, but as engineering projects whose footprints we can at least in principle look for. We ask not whether some cosmic parent loves us, but whether certain regularities in data would be easier to explain if long-lived control systems existed. Take asteroid statistics as an example. We already catalogue near-Earth objects and model their source regions. Over time, we can measure how many cross certain distance thresholds and how often large impacts occur. If, over many tens of millions of years, the rate of truly catastrophic impacts is lower than random models predict, and if that deficit is concentrated around one particular planet rather than shared evenly, that would be interesting. It would not prove intervention, but it would raise the question. Similarly, measurements of radiation belts and cosmic ray flux could, in theory, show patterns of shielding that are unusually efficient. If Earth experienced fewer high-energy particle events than its position in the galaxy and local environment would suggest, especially in ways that benefit surface life, that too would be a clue. Right now, our data span too little time and too few comparable planets to say much. Almost all we can do is outline the kind of evidence that would shift probabilities in one direction or another. There is another layer to this speculation that pulls our focus beyond Earth. If a civilization figured out how to weave protective and computational structures into the space around one planet, nothing stops it from extending that pattern to others. In fact, once you understand field control at that level, there is a strong incentive to build a network. You can stabilize asteroid belts, shepherd comets, and synchronize climates across multiple worlds. Over astronomical periods, such a network could even serve as a beacon, its rhythms distinguishable from natural variations when observed from afar. From this angle, the solar system becomes not just a random collection of rocks, but a potential node in a much larger architecture. Planets with similar patterns of impact avoidance, field behavior, and climate resilience might form a recognizable signature of membership. We are only just starting to gather the kind of comparative data that would let us test such ideas by studying exoplanet atmospheres and environments. If we ever saw another system where several planets show synchronized, long-term stability that defies simple models, we might be looking at evidence for a guardian network in action. Bring this back down to us, here and now. We do not see obvious shields in the sky. We do not have clear evidence of trajectory nudges or field modulation beyond what natural physics predicts. Yet Earth has been remarkably hospitable for an incredibly long time, through asteroid storms, solar variability, and internal convulsions. Is that just the lucky outcome of robust natural feedbacks? Or is there more to the story? The honest answer, based on current science, is that natural explanations are enough. Plate tectonics, the carbon cycle, and biological feedbacks can account for much of the stability. But the Silurian hypothesis whispers that we should not stop at enough. We should be willing to entertain the possibility that we are living under the tail end of a protective system built long ago, one that has been running in the background like a planetary autopilot, indifferent to who benefits as long as the biosphere continues. If that were true, it would raise a profound question about our role. Are we unexpected passengers on a ship whose course was set by someone else? Or are we the intended successors, meant to eventually take over the controls? Either way, our increasing ability to detect, and perhaps one day manipulate fields and orbits, puts us on the edge of the same power. We are learning how to deflect asteroids, how to model and predict solar storms, how to think in terms of long-term planetary risk. In a sense, we are inching toward the job description of invisible guardians ourselves. The final twist in this story is that any such guardianship, whether inherited or newly built, is meaningless without understanding. You could be protected for eons without knowing why, only to squander the opportunity in a few centuries of reckless industry. To avoid that fate, you need more than shields. You need guidance, context, and a sense of where previous civilizations went wrong. If those stories were preserved anywhere, they would be the most precious artifacts of all. In the last part of this journey, we will turn directly to that possibility. We will leave behind isotopes and orbits and ask whether there are messages embedded in our planet's history, in myths, in mathematics, or in subtle patterns of information that look less like random noise and more like advice. Advice from whoever or whatever may have built the systems that keep this world so strangely habitable. And we will have to confront a final choice, one that no earlier civilization may have managed to get right. If there really were guardians, The most valuable thing they could leave behind would not be shields or machines. It would be context. A record that says this has happened before. Here is how it usually ends. Here are the traps you keep falling into. And here are the doors that almost nobody notices. Without that, even the best protection just buys time for you to repeat the same mistakes with bigger tools. So if we are going to take the Silurian idea seriously all the way to the end, we have to ask a final, uncomfortable question. If someone tried to warn us, where would they have put the message? And how would we recognize it as anything more than noise? The most obvious place to look is in the rocks and ice themselves. Earth already keeps a detailed diary of climate, chemistry, and catastrophe. We have learned to read some of it through isotopes, trapped bubbles of ancient air, and subtle shifts in mineral structure. If a civilization wanted to leave a message for any future species that learned geology, it could have encoded information in layers that stand out. A thin band with a deliberately strange combination of elements or ratios that do not match any known natural process. A sequence of layers that forms a pattern, a kind of barcode stretched across millions of years. We already see some intriguing repeats in the record. Ice ages come and go with a rhythm driven by orbital cycles. Carbon levels wax and wane with plate tectonics and biological evolution. Mass extinctions cluster in ways that reflect the deep structure of the planet. When you first encounter these patterns, they can feel almost scripted. But once you understand the physics, most of the mystery evaporates. The cycles arise from gravity, feedbacks, and chance. To make the case for deliberate design, you would need something that refuses to yield to natural explanation, even after careful study. So far, science has not found such a stubborn anomaly in the geological archive. That does not mean one is not there. It just means the data we have and the tools we use have not demanded a technological interpretation. The Silurian perspective turns that into a challenge. It tells us to keep refining our models and measurements until we can say with more confidence whether any layer or sequence looks like a deliberate information carrier. That work is slow and patient. It is also the same work we need for understanding climate and extinction for our own sake. Beyond rock and ice lies a very different kind of archive, the one we carry in our stories. Every culture on Earth preserves myths about floods, fires, golden ages, and lost worlds. They talk about beings that came from the sky, brought knowledge, and vanished. They tell of cycles of rise and fall, of hubris and punishment. For a long time, scholars read these tales as reflections of human psychology and local disasters. Then, in some cases, they discovered geological events that line up surprisingly well, like sudden sea level surges after ice dams broke at the end of the last ice age. It is tempting to see such alignments as evidence that myths are just garbled memories of real natural events. That is certainly true in part. Oral traditions can preserve echoes of earthquakes, volcanoes, and meteor impacts for thousands of years. But if we are willing to entertain the idea of much older civilizations, we can also ask whether some story motifs might be cultural shadows of contact with something far older, not direct memories, which would never survive across tens of millions of years, but patterns that recur because they resonate with a deep structure in how technological societies live and die. Think about how often we tell ourselves the same kind of cautionary tale. A people discovers powerful forces, uses them carelessly, and brings ruin on themselves. A city rises to incredible heights of wealth and influence, then collapses under the weight of its own arrogance. A guardian figure warns of danger, is ignored, and catastrophe follows. These stories show up in different forms from one culture to another, but their bones are similar. We explain that through shared human experience and shared brains. Our minds are tuned to care about hubris, justice, and survival. From a Silurian angle, though, those motifs become more than psychology. They look like a possible language for passing warnings down the line. If you cannot literally tell future species about your mistakes, you can at least expect that any intelligent beings who face similar challenges will rediscover the same narrative shapes. They will write tragedies about overreach and comedies about foolishness. They will imagine guardians and tempters, cycles and resets. In that sense, myths are less like historical records and more like a mirror in which we see ourselves and maybe, faintly, those who came before. Then there is mathematics. Unlike a story or a rock layer, a mathematical object does not belong to a particular culture or planet. Prime numbers, geometric ratios, and fractal patterns are the same everywhere. That is why so many proposals for contacting extraterrestrial intelligence involve sending sequences of primes or diagrams of simple shapes. If you want to say this is not random, math is a good tool. If an earlier civilization wanted to leave a message for any future mind that can count and reason, it might have used mathematics embedded in nature itself. You already encounter something like that in fundamental physics. The constants that govern forces and particles have specific values. The ratios of certain masses and energies look finely tuned for the existence of long-lived stars and complex chemistry. Some researchers argue that if those numbers were only slightly different, galaxies might not form, life might not arise, or atoms might not be stable. This has led to ideas about a multiverse and anthropic reasoning, where we exist only in regions where the numbers happen to allow us. The Silurian hypothesis does not change that big picture. The tuning of physical constants is a separate question from the history of civilizations on a given planet. Still, there is a small space where the two could intersect. If a very advanced society learned how to manipulate the effective values of certain parameters locally, for example through engineered fields or exotic matter, it might be able to carve out regions of space that are particularly hospitable. The patterns left by that kind of work would be subtle. They might show up as small deviations from expected statistics in cosmic structures or particle behavior. Closer to home, mathematics appears in places that sometimes feel like puzzles. Spiral patterns in shells and galaxies, hexagonal tiling in basalt columns, recurring ratios in biological forms. We understand most of these as the natural outcomes of growth rules and energy minimization. They are beautiful, but they do not require a designer. If you wanted to hide a deliberate mathematical message, you would have to go beyond using the same structures that physics already favors. You would have to encode something that cannot easily be produced by blind processes. One idea that has been floated in the search for extraterrestrial intelligence is the possibility of a message written into the cosmic microwave background, the faint afterglow of the Big Bang. On a smaller scale, you could imagine something similar in the statistical structure of noise in a planetary field, or in the distribution of certain subtle features across space and time. These are not easy places to hide a message, but they are extremely durable. They would persist long after individual artifacts decayed. The cost is that they are also incredibly hard to decode without the right framework. All of this circles back to a sobering conclusion. If someone did leave messages for us, they may be so deeply entangled with the fabric of nature and culture that we have been staring at them without recognition. The lines between artifact and environment, warning and story, are blurrier than we like to admit. The Silurian hypothesis does not give us a clear treasure map. It gives us a way of thinking that sharpens our questions and reminds us that our data are always incomplete. At this point, it is worth stepping back and asking what we have actually learned on this long journey. We began with tiny metal spheres in ancient rocks and a playful question from science fiction. Could there have been another industrial civilization on Earth long before us? And if so, would we notice? We followed isotopes through natural reactors and imagined nuclear ghosts of old wars. We compared ancient climate spikes to our own and asked how visible industry really is on geologic timescales. We dove into the deep ocean and scanned nearby worlds for scars of machines. We treated life and minerals as potential hardware and considered the possibility of invisible guardians woven into fields and orbits. Each time, when we compared these ideas to what science currently knows, the same pattern emerged. Natural explanations are strong. The data we have do not require earlier civilizations. No obvious alien cities lie at the bottom of trenches. No lunar strip mines jump out in orbital images. No unambiguous technological signatures linger in ice cores from 50 million years ago. If there were predecessors, they left a far lighter mark than we are leaving right now. And yet, the exercise has not been pointless or purely imaginative. In trying to see others, we have seen ourselves more clearly. We have come to understand that even a brief industrial burst like ours writes itself into rock, air, and ocean in ways that will be detectable for millions of years. We have learned that some of the most durable traces are not buildings, but chemistry, and isotopes. We have realized that the line between technology and nature can blur, especially when life and minerals are used as infrastructure. We have glimpsed the scale of responsibility that comes with being able to influence not only climate and extinction, but orbits and fields. That realization puts us at a decision point. If we are, in fact, the first technological civilization on this planet, then we are writing the opening chapter of a story that could last as long as Earth remains habitable. If we are one in a series, then we are one of the few species to reach this threshold, and the record suggests that most who do fail in ways that leave only faint traces. Either way, the choices we make in the next few centuries will determine whether our civilization becomes a thin radioactive ring and a burst of plastics in the fossil record, or the seed of something that endures and matures. You can frame that choice in many ways, as a question of ethics and fairness across generations, as a challenge of engineering and governance, as a competition between short-term desires and long-term survival. The Silurian perspective adds one more layer. It invites you to imagine that the planet has seen this pattern before, that the same temptations and blind spots, the same rush toward power and growth, have played out in earlier forms. It asks whether we are willing to learn from that imagined history, even if we never find direct proof that it happened. In practice, learning from it means paying attention to the durable markers we have discussed. It means treating carbon dioxide and synthetic chemicals not just as emissions, but as geological signatures. It means thinking about nuclear technology not only as a risk in the present, but as a message to whoever comes after. It means designing our infrastructure with an eye toward integration with natural cycles rather than domination over them. It means asking whether we can build a civilization whose long-term footprint looks more like a gentle modulation of planetary processes and less like a sudden shock. There is also a more intimate dimension. On some level, the Silurian hypothesis is about loneliness and kinship. When we ask whether we are the first, we are really asking whether anyone has ever walked this path before us, felt this mix of power and fragility, and tried to navigate it. Even if the answer is no in a strict factual sense, thinking as if the answer might be yes can shift our attitude. It can make us feel less like rulers of a new world, and more like apprentices in a very old workshop, one where the tools are dangerous and the lessons are written in very small print. So where does that leave us? We stand on a thin skin of rock, under a layer of air we are actively changing, in a solar system that might be nothing more than a random patch of cosmic real estate, or might be part of a vast, quiet network. Our species has lit up the night with cities, laced the oceans with cables, and started to touch other worlds. We have also destabilized climate, driven extinctions, and created technologies whose downsides we barely understand. We are visible enough to leave a mark in the rocks, but not yet wise enough to know what mark we want that to be. The Silurian hypothesis does not tell us whether someone else solved this puzzle in the past. It certainly does not guarantee that we will. What it does is remind us that the question is bigger than our own comfort, or even our own species. A technological civilization is not just an event in human history. It is an event in planetary history. It changes how a world evolves and how it might be perceived from beyond. Treating our moment as unique in the strongest sense is probably a mistake. Treating it as precious is not. At the end of this long thought experiment, we are left with a paradox that is both humbling and empowering. We may never know with certainty whether Earth has hosted other industrial ages. The traces, if they exist, may be too subtle or too well erased. But we can be absolutely sure that any future investigator who looks back at our time will see something unusual. A sharp spike in carbon, strange isotopes, synthetic molecules, and perhaps a brief glitter of metal on the seafloor and dust on the moon. They will know that for a little while, a species here reached into the deep structure of the planet and the sky. The open question, the one only we can answer, is what story those investigators will tell about us. Will they see a civilization that flared up, burned hot, and vanished, leaving behind warnings nobody was around to read? Or will they see the early chapters of a long, slow transformation in which technology sank into harmony with geology and biology instead of fighting them. We do not get to erase our presence from Earth's memory. We do get to decide whether that memory reads like a cautionary tale or the beginning of a very different kind of history. In that sense, the Silurian hypothesis is not really about ancient reptiles or speculative empires. It is about a mirror we hold up to ourselves, one that stretches across millions of years. When we look into it, we are invited to imagine both our own fragility and our potential to become the kind of civilization that could leave gentle guidance instead of scars. Whether or not anyone did that for us, we still have the chance to do it for whoever comes next.